Hello everyone. Today our topic is design of combined trapezoidal footing. So I'm just going to write down the topic name, design of combined trapezoidal footing. So what will I do is I will actually take up one problem, one numerical, and as we move along, like as we progress with the numerical, with the steps of the numerical, we'll be discussing the theory parallelly. So like at one time, your numerical will be done and all your theory will also be done parallelly. So I'll go like that. So let us take a numerical for that. Design of combined trapezoidal footing. Basically, trapezoidal footings are required when suppose we have restricted space, basically. When we have restricted spaces to adjust to. So now, for a combined trapezoidal footing, let us take a set of data. Okay, suppose there are two columns, C1 and C2. So C1 and C2, both are 350 by 350 mm, 350 by 350 mm size. Okay, and C1 has load 350 kilonewton and C2 has load 750 kilonewton. Okay, so that kilonewton load, I will take it as P1 and P2. Now, the spacing between the two columns are like 2.5 meter center to center, center to center spacing. Okay, and extension on the heavier column, on the heavier side, should not be greater than 1.5 meter. Okay, that means beyond C2. C2 is the column with the higher load. So it is said that beyond C2, you cannot extend it further than 1.5 meter. So extension beyond C2 should be less than or equal to 1.5 meter. It should not be greater than 1.5 meter. So in those type of cases where you cannot extend the edges, okay, or like the extensions are limited, in those cases, like we use the trapezoidal footing. Okay, so now there is a central beam which is of 400 mm width, central beam, and SBC of soil is given. SBC is given 150 kilonewton per meter square. So this is the ultimate data set for the numerical. Okay, so we will now try to start solving it. So let's try to just draw a preliminary diagram. How will it actually look like? Okay, so basically, if I look into it, this C1 will be like this, then C2 is like this. Between them, the center to center distance is 2.5 meter. Center to center distance is 2.5 meter. Then extension beyond C2 is 1.5. You cannot extend it more than 1.5. So now what we do, we assume extension beyond C1. We have to assume some extension, right, on the left of C1 is equal to half of the radius. half of the size of the column. Okay, half of the size of the column. So it becomes 0.175 meter. That means we are taking an extension which is like around 0.175 meter. That is assumption. Okay, we are taking it as half of the column size. Okay, I am not drawing it to scale. The column size is 0.35. So I'm not drawing it to scale, but it is just a representative diagram. So I think you have understood what I am trying to represent. Okay, so now, okay, so uh, total load we know. So area, yes, one thing I forgot. When you find out the area required, you have to also add self weight along with the total load. So self weight will be considered self weight. We don't assume the self weight. We don't calculate the self weight accurately. We just take it as 10% of the total load. This takes care of the self weight. So we don't measure the self weight of the whole system. Okay. So now total load will be taken inclusive of the self weight. So total load now becomes 1210 kilonewton. Okay. Now 1210 kilonewton. If I divide it with the SBC, so you will get the area required. 1210 kilonewton divided by SBC, which equal to how much? The value becomes around 1210 divided by 150. So it becomes, let me calculate it, 8.01, 06, 8.06, 066, or you can say 8.07 meters square. Okay, so this you keep in mind. Area is 8.07 meters square. Now, let us go back to this screen where we have drawn the center to center distance between the columns and all. Okay, now let us try to like draw it further. You see, if this is the footing, suppose, okay, if we have to represent the footing here, suppose the footing will be somewhere like this, and obviously, like it will be something like this, okay, something like this. Obviously, it will not be like that of a rectangle, but let me again. It will not look like a rectangle, sort of, because it is a trapezoidal footing. Let me just mark it a little bit more accurately. So basically it will look like this. I'm not drawing it to scale, so obviously my drawing will be a little bit different. Okay, so you please try to draw it more accurately. Okay, I'm just drawing a representative diagram. So what will be the length of this footing right now? Length will become 2.5 plus 1.5 plus 0.175. It becomes equal to 4.175 meter, which is equal to length. Okay, this is the length of the trapezoidal footing. Okay, so now let's proceed further. So length we have got 4.175 meter. Okay, so one more thing we have to find out, like when the columns are, suppose this one is C1 and this one is, we know this one is 2.5 and this one is C2, having like 350 and 750 kilonewton load. The main funda that I have to like actually take into account while designing the footing is that the resultant of the load, resultant of the load must fall to the CG of the footing. That's why when we calculate rectangular footing, since rectangular footings are like symmetrical, so in rectangular footing, we take the resultant of the load at the midpoint. But in trapezoidal footing, since the dimensions are irregular, we have to actually calculate. Okay, we cannot directly keep the resultant of the of these two loads at the midpoint of the trapezoidal footing. We can keep the resultant of the loads at the midpoint of a rectangular footing, but not at a like midpoint of a trapezoidal footing. So now let us first find what is the resultant relative to this C1. What is the location of the resultant relative to C1? Okay, suppose I take it as X. It will be nearby 750 because 750 is the larger load. Okay, so how will we calculate the resultant now? So it's very simple. It's a simple formula. Okay, it's a simple formula. So we'll simply write down the formula to find out the location of the resultant. Okay, so here it is. It will be 350 into, if I take it, its location as 0. Okay, 350 into 0 plus, and if I like, just wait a second, take the, for 750, the location is 2.5. So divided by 350 plus 750. This is the way in which we actually calculate the location of the resultant. So you calculate it, you see how much it comes. You do you also try it and see the location it becomes. You just calculate and check into 2.5 actually 50 plus 7. So 1.70. Okay, 1.70. 0.705 to be more accurate. So this X is actually 1.705. Okay. Now let me draw the footing again, combined trapezoidal footing again, but this time in a little bit more of detail. So it's like this, like this, like this, then C1, then C2. Okay, so this we have already got 4.175. Now this was 2.5 and this was 1 point, resultant is 1.705. So maybe like somewhere here. So the resultant is falling somewhere here. Okay. Resultant is falling somewhere here. So this we know, this is 0.175. So what is this location? This location is how much? This location is 1 point. It becomes approximately 1.88. 1.88. So overall for the trapezoidal footing, if I consider this size as A, this size as B, and this 4.175 as L, this resultant of the two loads, this location 1.88 should also be the CZ of the footing also. Okay, CZ of the footing, the resultant always must fall through the CZ. That's why I told you when it was rectangular footing, we take the resultant at the midpoint of the footing, rectangular footing, because it is rectangular, but here it is trapezoidal. But so we don't know exactly where the resultant is falling. So we'll now adopt a few formulas. Okay, so how we know the resultant? Suppose 1.88 is for the trapezoidal footing, it is XR, suppose resultant, the CZ location. So now this XR is this one, suppose XR, it should be the CZ, right? So if this is A, I'm drawing it again and again for your own convenience. If this is B, means XR should, the location of the resultant should fall at the CZ. That is our prime importance. So the XR formula is actually L by 3 into A plus twice B into A plus B. If I do this calculations, okay, actually we need, our main aim is what? L, we have got. A and B we need, because A and B we have not yet found out, right? And one more formula we can make. See, A and B are two variables, so we need two equations. So one equation we have already got, and XR we know, L we know, A and B we don't know. So one more equation if we can find out for A and B. So two equations, two variables we will get. So we can solve it then. So we can take it one equation for the area. Area is what? Half into area of a trapezoid. So it is half into sum of the two parallel sides. Okay. Sum of the two parallel sides, A plus B, into distance between them. Here also A you know, 8.07, L you know, A plus B you know. So we get two equations. This is second equation. This one is first equation. Okay, so now we solve this two. We solve this two equation and we get the value of A and B. So you do it yourself. Okay, so let me just do a few steps. A is equal to, you know, half into A plus B into L. This implies A plus B is equal to twice A by L. 2 into 8.07 by 4.175. So you calculate how much it becomes. I'll just do the calculation. 2 into 8.07 divided by 4.1. It becomes 3.86. That is one equation. A plus B is equal to 3.86. This is like the second equation, isn't it? So that was the second equation that I gave you in just the previous slide, right? You have got it. Then now you go to the first equation. We get xr equal to, we know, L by 3 into A plus twice B into A plus B. So this implies I put the values 1.88 is equal to 4.175 by 3 A plus twice B by A plus B. I can take it from equation number 2, 3.86. Now if I solve it, what will I get for A plus twice B? Just I'm solving it and I'm telling it to you. 1.88 into 3 into 3.86 divided by 4.175, 5.21. Once again, I'm just going to recheck it. 1.88 into 3 into 3.86 divided by 4.175, 5.21. Okay, 5.21. So we get this as equation number 1. Okay. So A plus twice B is equal to 5.21. A plus B equal to 3.86. So this one was, if I again just rename it as equation A and B, A minus B, B implies B equal to how much? 5.21 minus 3.86. 5.21 minus 2.86. It becomes 1.35. And if I put this value, suppose here, so A will be equal to 3.86 minus 1.35, which is equal to 2.51. Now, we have got that A is 2.51 and B is 1.35. But in this case, A becomes greater than B. But our assumption in the drawing was A was smaller than B because A was near the column having the smaller load, right? Because A was near the column having the smaller load. This was C1. This was C2. So A should be smaller. But we got A greater. So what we do is now our like it is contradicting our assumptions. So what we do is we flip the values. Okay, we put the value of, we exchange the values A and B. A we are I take A as 1.35 and B as 2.51. A as 1.35. Wait. And B as 2.51. Just I'm rechecking it. 2.51 and is 1.35. Now you see, that means now we are flipping it. Okay, sorry. So now what we get, what we have to check is, like, if by flipping the values, okay, now the trapezoidal footing, that we get. Suppose this one was the trapezoidal footing. This one was C1, this one was C2. This one was the resultant somewhere. So 1.88. A becoming 1.35 and B becoming 2.51. And L we already know. If now this resultant equation XR, which is equal to XR, we know XR is 1.88. CZ formula is equal to L by 3 A plus twice B by A plus B. Okay. Now, if I put the new values of A and B, which is 1.35 and 2.51 in this equation, and get a new value of XR, if it is somewhere near to this 1.88, through which this 100 load actually is falling, then we can say that yes, almost fine. It can be flipped. The main intention is that the resultant of the two loads, 350 and 750, 1100, should fall to the CZ. So our main intention is to keep the CZ near the resultant. So if A is 1.35 and B is 2.51 and the resultant location we have seen it is 1.88 from this edge, from the left, if it is near, then we can say that these are sufficient. So let us now do that. Okay. So XR equal to 4.175 by 3 into A plus twice B, 35 plus 2 into 2.51 by 1.35 plus 2.51. Okay, just I am checking it. A was 1.35 and B was 2.51. So L by 3. Okay, now you solve it and see like what is the value of XR. So I am just solving it. 175 by 3 into 1.35 plus 2 into 2.51 divided by 6. Last time checking it once again, 1.2 plus 2 into, it becomes 2.29. There's 2.29 meter. So when we flip the values, the CZ actually falls somewhere around 2.29. That means this is around 1.9 and this is around 2.3. So 2.3 will be somewhere here. 2.29 or 2.3 will be somewhere here. Okay, somewhere here. This CZ. Okay, 2.29. So almost near. Okay, almost near. So we can say that yes, fine. We can flip it and we can actually like keep these two values. Okay. Or if you want to like do some more trial and error, what you can do is like to bring this 2.29 more closer to 1.88, you can just increase this 1.35 to maybe 1.4 maybe or 4.5. Okay, and this you reduce this 2.51 you reduce to 2.35 maybe, and you check that means you increase a little bit and you decrease B a little bit because you want to shift this XR value a little bit to the left near 1.88. So if you have to shift the CZ to the left, earlier it was at 2.29. Now you have to bring it to, from 2.29, you have to bring it to 1.88. So you need more area on the left so that it can bring the CZ a little bit to the left. So increase the length of A a little bit and decrease the length of B a little bit so that some more area shifts to the left, so that ultimately the resultant becomes more like near, okay, to the CG. So this is how you do the trial and error. Okay. Now you can keep it with 1.35 and 2.51 also. Okay. So because this 400 mm is okay. It's like it may not make such a difference. Okay. So today we will stop at the sizing, preliminary sizing. Next, we will be discussing the design. Okay, design of the beam. Okay, central beam is there, and just a few things are there. Reinforcement of the central beam, and how to calculate the reinforcement through calculation of the moment and shear force. That we'll discuss. Okay, so I am dividing this into two parts, part one and part two. Part one refers to like is related to mainly the sizing, how you find out the sizes of the footing, trapezoidal footing. Okay, so thank you for now.